Hello and welcome to this most wonderful time of the year. The Advent of Code is here. If you don't know what is Advent of Code, it's an advent calendar of programming challenges that open up every day for 12 days in December. Enjoy the fun, try solving those problems on your own, and then of course you can come back to me and let's compare the solutions. But today we will start with day 4. So last time we fixed the escalator and went down to the printing department. You ride the escalator down to the printing department. They're clearly getting ready for Christmas. They have lots of large rolls of paper everywhere, and there's even a massive printer in the corner to handle the really big print jobs. Decorating here will be easy. They can make their own decorations. What you really need is a way to get further down the North Pole base while the elevators are offline. Actually, maybe we can help you with that, one of the elves replies, when you ask for help. We're pretty sure that there is a cafeteria on the other side of the back of the wall. If we could break through the wall, you'd be able to keep moving. It is too bad all of these forklifts are so busy moving those big rolls of paper around. If you can optimize the work the forklifts are doing, maybe they would have time to spare to break through the wall. The rolls of paper, @ are arranged on the large grid. The elves even have a helpful diagram, your puzzle input, indicating where everything is located. For example, this is a sample map. The forklifts can only access the roll of paper if there are fewer than 4 rolls of paper in the 8 adjacent positions. So if you look, for example, at this one, in the 8 directions, this would be 1, 2, 3, 4, 5, 6, 7, 8. So in this case, there is 1, 2, 3 adjacent, so it's accessible. So here in the example, we can see the same thing. The first one, those two are accessible. This one is not because it got 1, 2, 3, 4, 5, 6, 7 neighbors, which is more than 4. Okay, consider your complete diagram of paper roll locations. How many rolls of paper can be accessed by forklift? So we need to find out how many of them can be easily accessed. I have already solved it, that's why I have my answer, but for you it will be an input that you need to provide to earn your first star of the day. So this is a great opportunity to try out different languages that you are not really used to. For example, for me it's Go, but you're free to use any language that you want, but I still encourage you trying something new. Okay, as always, I will define a function part1 that will accept an input. In this case, it will be a grid of strings, and we need to return number of how many rows are accessible. And by default, let's return 0. And again, to make things simple, I'm breaking down problem into smaller chunks that I can write tests for and verify that they are working, like in TDD approach, because the Advent of Code is usually about some edge cases, and if you're looking for bugs in your basic steps, it will be a waste of time when bug could be in somewhere for larger logic. So let's verify that things work before we proceed further. I want to have a function that will tell if this roll of paper is accessible. I will have my grid, and I will have 2 positions, row and column. And we'll return a boolean saying yes or no. So the only thing that we need is count neighbors. In this scenario, we have our grid, and this is our window that we are interested in. So this will be our row and column at which we are currently looking. And we need to check each of these cells and count how many other rows are there. So from the coordinates perspective, it means 1 row above all of these lines would be row -1, and here would be row +1. Here row stays the same, but now columns increment from left side to right side. So in this case, it's column -1. Here it also is column -1, column -1. Here it's just the same column. And here column +1, column +1, column +1. Technically, we could just have 8 if branches and calculate for these positions, or we could create a nested loop which would go over 3 rows and 3 columns, ignoring the middle one. But we need to be careful because we could end up at a scenario where this window is actually overlapping the grid. which means that we don't always start with -1. We need to check if it is larger than 0 if we're checking the left side. If we're against the top, we also need to check if it's larger than 0. But if we are here overlapping the right side or down, we need to be sure that we are not going over the grid's width and grid's height. So for that, I will define here a start row. So start row here will be either the maximum is the row -1, or it will be the 0, right? Because if you're going over this side, it means that we have crossed it, it will become negative. So we need to go to 0 back. The end row would be then the other way around, the minimum value. Either it will be the row +1 or the length. Same goes for start column. It will be either column -1 or 0, and end column the same approach, just with the length of the first row. Okay, now from the start row to go over through all of these columns. If they are equal, we continue because it means it's the center. But if not, then we look and we need to count the total number. So total access, so total, or let's call neighbors. Neighbors is 0. And then here we check if the grid current row and column equals to this add symbol, we increment the neighbors count. And now the grid. And we say if the neighbor count is less than 4, it's accessible. Okay, looks good. Let's define a test for it. Let's have test is accessible. Let's define some sort of one grid, and let's have some proper couple of examples. So for example, here, this one is accessible because there is no issue, for example. This one should not be accessible because it has 4 neighbors, 1, 2, 3, 4. Then we can have here similar pattern. And let's keep for now this simple and check following scenarios. So test would be row, column, and expected state. And I'm saying the 0, 0 is accessible. It does not have more than 4 neighbors. 0, 1 is not accessible because it has 4 neighbors. Then this one, 0, 2 is accessible because it has only 3. Then this one is 1, 1, and it is not accessible. Okay, let's test here. Let's test this out before we proceed any further. Then for each of these tests, let's run it. It's accessible. And if it's not correct, we throw an error. Just like that. Let's run the test. And we can see all of these scenarios matches. So the correct way would be also the mirror test cases, because we could go wrong over the border. So 4, 3 should not be accessible. The 4, 4, this one should be accessible because it only has 3 neighbors. Okay, let's leave like that. So we are pretty sure that this part works. Okay, now for the implementation itself. So our goal is to find the accessible count. We need to go over all of the grid elements and check if it's accessible. But we have missed one, I think, part, which actually is that we only check for the roles. So we need to here check if actually the thing that we are checking is role, and then if it's accessible. Okay, let's run the sample input. Test part 1, sample input. Okay, so our input will be these strings. Let me copy over the sample. Okay, looks correct. Now here missing brackets. So this is our input. So expected count result, and let's compare it and throw an error. The only that we need to have here, there are 13 accessible roles in the first sample input. Let's run it. Success. Let's run it now on our input and get the possibility to earn our first star. So we will read the contents of file, which is the input. Then I will take the input. I will first convert the bytes to strings. And then I need to actually also split this string by new line, and I'm on Windows, I will need to add /r. Okay, looks good. Now just the naming here, puzzle input, and the expected value. For me, it's already known. Okay, the big moment of truth. 1, 2, 3. And success! We have earned our first star of the day. Now let's go over to part 2. Now, the elves just need help accessing as much of the paper as they can. Once a roll of paper can be accessed by forklift, it can be removed. Once a roll of paper is removed, the forklifts might be able to access more rolls of paper, which they might also be able to remove. How many total rolls of paper could elves remove if they keep repeating this process? Aha! So we need to, when it's accessible, we remove it and run again our algorithm. Starting with the same example as above, here is one way. So these are first 13 available, so they are removed, and then they free up new one. And the question is how many rolls of paper in total can be removed by the elves on their forklifts. I mean, if you're not looking for the quickest solution, I would say let's just run the same part until there are changes happening to it, right? So if I would take the part 2, and now the logic here stays the same, but I will introduce a variable has changed something, let's call it like that, which initially will be true. So while the has changed something happens, I need to repeat this process. I can here say has changed something is false initially until proven otherwise. Then instead of the accessible count, I need to count removed, which in this case would be, okay, I'll go over the grid. If the grid is this element and it's accessible, I will remove it and tell that something has changed. But we also need to replace the symbol by the, for example, dot. It's not mutable in such way. Then let's just combine it by these two slices. And now we return the remove count. Looks like that could be all. So one more time. We have a flag that checks if something has changed. Then we have the removed count. While something is changing, we say, okay, nothing is changing. We are assuming nothing will change in this iteration. Then we do the check. We found that this is removable. We remove it. We say, okay, indeed something has changed. And then we replace the symbol with the dot so it does not mess up with the further results. Okay, I mean, that could be actually it. Let's test it on the sample input. So part 2 sample input, we run the part 2, and the expected value should be 33 this time. And success! Yeah, looks like that is all that it's needed. So now, the big question, will it work on the puzzle input and provide us the correct result? So part 2 on the puzzle input, let's go with the part 2. You again will not know the correct answer for the part until you find it. For me, I already know that it will be this number. Let's count together. 1, 2, 3. Yay! And success, you have solved day 4 and earned another 2 stars into your collection. For now, this looks like it was the simplest day. Let's see what will be tomorrow. Until now, for me, I think was the simplest day. What was your experience? Let me know down in the comments. Let's see what the day 5 holds. Of course, try it first on your own, then you can come back to me and let's compare the solutions and leave comments how you experience it. Maybe you have some clever solutions, clever ideas that could be used to solve it differently. I would gladly hear about them. If you like what you see, leave a like, subscribe so you don't miss the next video. But until then, keep coding and I see you tomorrow.